We're surrounded by all sorts of invisible forces, right? But I'd argue that few are as powerful or as misunderstood as ionizing radiation. It literally comes from the very heart of the atom. And in this explainer, we're going to unlock its secrets.
So, how do you even begin to wrap your head around something you can't see or hear or touch? Well, we start with a simple question. What is this invisible energy? We're talking about something that comes from the absolute core of matter itself, the atom.
Okay, so it all starts with an unstable atom. Just think of it as being a little too energetic for its own good? It's got this excess energy. And to find its balance, it has to shed it. And it does that by releasing a burst of particles or waves. And that is what we call radiation. Now, to be really precise, we're talking about ionizing radiation. And the clue, the really crucial part, is right there in the name. It has enough energy to physically knock an electron clean out of another atom it hits. When that happens, it creates something called an ion. This whole interaction is what gives this type of energy its unique properties and, well, its power. So this energy gets released in a few different forms. First up, let's look at the ones that are actual physical particles. I'm talking tiny bits of matter getting shot out at incredible speeds. So let's meet the two main players here. First up on the scene is the alpha particle. You can think of this one as the heavyweight of the group, the real bruiser. So what exactly is an alpha particle? It's actually not as exotic as it might sound. It's just a little packet of 2 protons and 2 neutrons. I mean, it's basically the nucleus of a helium atom, just launched at a super high speed. And because it's this big, heavy particle, it doesn't travel very far. It gets tired out pretty quick. It's easily stopped by just a few centimeters of air, a single sheet of paper, or, get this, even the outer layer of your skin. So what does that mean? It means the real danger is internal. If you were to somehow inhale or ingest something that emits alpha particles, that's when its power can cause direct damage to your cells. All right, next up, we've got a particle with a totally different personality, the beta particle. So if the alpha particle was our heavyweight, then the beta particle is the speedster. It's this tiny electron-like particle that gets shot out of the nucleus when a neutron randomly decides to turn into a proton. It's way, way smaller and lighter than an alpha particle. And because it's so much smaller and faster, it's way more penetrating. It can travel a lot further in the air. It'll zip right through a piece of paper, no problem. It can even get about a centimeter into your skin, and that's why it can cause some nasty skin burns. To stop this little guy, you're going to need something a bit more substantial. Think a piece of wood or some plastic. Okay, so we've met the particles, the heavyweight, and the speedster. But you know what? That's only half the story. See, radiation isn't always a physical thing. Sometimes it's just pure raw energy. And that brings us to gamma rays and X-rays. I kind of like to think of them as the ghosts of the atomic world. Why? Because they have no mass, no charge, just pure energy moving at the speed of light. Spooky, right? So a lot of the time, after an atom spits out an alpha or beta particle, its nucleus is still, well, it's still a little jittery. It's in an excited state. And to finally calm down, it releases one last burst of pure energy. That burst is a high-energy photon, and that is a gamma ray. Now, the thing you really have to understand about these guys is their penetrating power. It's off the charts. Because they have no mass and no charge, they just slice right through matter. Paper, wood, yeah, that won't do a thing. To stop them, you need really thick, really dense stuff, like lead or concrete. And that's what makes them such a serious external hazard. They can pass right through your body, damaging cells all along the way. And just to put this all into perspective, gamma rays are part of the very same electromagnetic spectrum that includes the visible light you're seeing with right now, and even radio waves. The only real difference is energy. They just pack so much more punch into each wave that unlike regular light, they have that power to knock electrons from atoms. And that right there is the key to what makes them ionizing radiation. Okay, so we've met the whole family now, right? We've got alpha, beta, and gamma. Let's bring it all together and do a little side-by-side comparison that's going to make the practical differences crystal clear. This chart really lays it all out, doesn't it? The big, bulky alpha particle, stopped by paper, so it's mainly an internal hazard. The zippy little beta particle, you need wood to block it, so it's a risk to your skin. And then there's the ghostly gamma ray that needs thick lead or concrete, which makes it a serious external hazard. Honestly, understanding these three key differences is pretty much the foundation of all radiation safety. So, why does all this matter? I mean, why go through all the trouble of understanding these different types? Well, it's because these fundamental principles are exactly what allow us to safely harness this incredible atomic power for our own benefit.
And of course, the most obvious example is nuclear power. Inside facilities like these, scientists and engineers are controlling chain reactions that release this atomic energy. We then capture that energy to generate clean, reliable electricity. It's all about managing these incredibly powerful forces with absolute precision. But you know the saying, with great power comes great responsibility. The entire nuclear industry is built on a foundation of safety. We're talking everything from massive engineered shields to super strict protocols. And this is really crucial, carefully calculated limits on how much radiation workers can be exposed to.
So, what does a limit actually look like? Well, here's a key number from the UK regulations. If a worker is likely to get an effective dose greater than 6 millisieverts in a single year, they become officially classified. And that triggers a whole lot of extra monitoring and health checks. It's basically a line in the sand, and it's all designed to keep people safe.
And why do these limits matter so much? Because if you get really, really high doses, I'm talking thousands of times higher than any worker would ever normally receive, the effects are direct and predictable. Things like skin retting. The entire system, every single rule is designed to keep exposure so incredibly low that those kinds of acute effects just don't happen. They're prevented from the get-go.
So the next time you see a facility like this, just remember what's actually happening inside. Through some amazing science and engineering, we've taken this invisible, incredibly powerful force of nature, and we've put it to work for us. And we do it all while managing it with layer upon layer of safety and control. So think about the journey we've just taken. We went from a single unstable atom all the way to the massive engineering it takes to harness its power safely. We figured out how to shield ourselves from the particles and how to ride the energy waves. So the big question for the future is this: as our mastery of the atom keeps growing, how are we going to choose to use this immense power? What new doors is it going to unlock for us?